I'm a professor in atmosphere and ocean sciences at the University of Colorado Boulder. I've been doing Arctic research for about 20 years. And I just want to share some insights and some things that I think are really amazing and cool. First, I want to share this resource. It's called Worldview. Basically, what this does, it's a website here listed at the bottom. It stitches together visible imagery from satellite data and makes sort of a mosaic or a composite so that you can really get a sort of broad view of what's going on. So this is a view of the entire Arctic Ocean. So you can see, you know, the central Arctic here, which is an ocean covered with sea ice. There's also a lot of clouds. You see the Greenland ice sheet. You know, if you're, you know, teaching in North America, you know, you could always reference like, where are you on this image? But I think it's really nice because it's, you know, exactly what you would see if you were up in space looking down with your eyes. So it's reflected sunlight, visible light, and you see the complexity of this environment, the Arctic environment. So I think that's also nice for the students to see. And this was actually taken on June 1st, 2020, so just a couple days ago. And you can see most of the Arctic Ocean has sea ice cover on it still. If we look back, so this is a similar mosaic. Again, you can pick different times. This is from September 18th last year, the 2019. And you can see, you know, here when we look, for example, north of Alaska, we can see actually there's a lot of cloud cover there still, but we see peeking through the cloud, these very dark patches of ocean. And actually these are these areas that are ice-free. And September is the minimum amount of ice cover in the Arctic Ocean. And so it's nice to just be able to see those things, see the difference, see the importance of something like clouds in terms of how much sunlight gets reflected back to you. So you can also zoom in on all kinds of different areas, for example, your own local area, you know, any area of the globe. And so I encourage this as a resource because it's just kind of cool to see what you see from space with your own eyes.
Hi, Jen. Sorry to interrupt you real quick.
Yeah.
Do you mind putting it in presentation mode so that?
Oh, sure. Yeah.
Cool.
Is that good?
Yeah, that's great.
Okay. Yeah. So I really like this anchoring question that you guys are answering because it's a question actually that scientists are really interested in. And, you know, we have some of the answers, but not all of the answers. And so I think the process that you go through with your students is really cool for that. And I want to emphasize that both observations and models are really needed to understand the answer to that question, and indeed to understand climate change and variability together. So this is actually a picture of my foot. I'm stepping into sea ice, and this was the first time I stepped on sea ice, and it was a rather traumatic experience because my foot actually sunk into the ice. Luckily, there was just a surface melt layer, so I didn't go all the way down to the bottom of the ocean. But that experience of actually being on the ground is, of course, super powerful, and your students will really engage with that in terms of understanding the importance and value of something like MOSAiC. But I think it's important to also just emphasize the importance of models of different kinds, the conceptual models that you guys are building, and then also numerical models, which I'll talk about a little bit here. And then observations of many different kinds, right? I mean, my perspective, my one boot on the ground here is not going to give me the entire perspective of how the entire Arctic is functioning. And that's why we need things like satellites, other long-term data sets that, and data sets with a lot of spatial coverage so that we have a sense of how things are going. And, you know, I guess you could always make an analogy to something like the current pandemic, right? You know, my experience is probably very different than your experience and very different than other people's experiences. And all of those experiences are super valid, but it's really only by understanding all of the data that we really understand what's going on. So some caveats here. Observations are incomplete. I mean, obviously my one boot on the ground is a very incomplete observation, But MOSAiC, it's just one track, 1 year. Even satellite data that go back 30 years, they provide a lot of perspective. But for climate change and variability, we're really looking at these multi-decadal, full spatial coverage. That's where we really learn the most about climate and climate change and climate variability. And models are helpful, but as you guys have seen in your process here, models are wrong, right? We're always updating them and improving them. And just because they're wrong doesn't mean they're not useful. And I think that's another thing to really emphasize with your students, that you can be wrong, but still learn a lot. And that can help you take it to the next level of learning. And models are just a way to organize your thoughts and organize conceptually. And I think that they're really important. So these lots of different ways to measure and understand the Arctic. So there was a question in the chat about, the radiometer from MOSAiC. How does that relate to the radiometer that's, on a satellite? Well, this is actually the instrument that was launched on the satellite in space to measure the radiation, the data that you guys have looked at, the long wave radiation and short wave radiation. The instrument is called the CIRES instrument, so the Clouds and Earth's Radiant Energy System. And here it is with, an engineer from Ball Aerospace preparing it to be launched into space. So this is the data source for the radiation data that provide this kind of long-term context. So I loved this comment about, ground truthing and understanding, satellite data with in situ data. I think that's a great thing to emphasize for your students, because satellites can provide that long-term, full spatial coverage perspective, but it's nice to be able to know that they're working well. And so in situ observations definitely help with that. I also want to mention another source of data that we haven't talked a lot about in this class, but I think is really important for providing a long time perspective, and that's ice core data. So we can, dig ice cores in land ice, so over Greenland. We can also dig cores in the sea ice, but the sea ice is not very old. The oldest sea ice is maybe only 6 years old. And so we don't get a long core, a long perspective from digging into the sea ice. Whereas if we dig into land ice, such as Greenland, year after year we have accumulation, and the air bubbles that are trapped enable us to look at the composition of atmospheric gases. We can look at things like dust. So that can provide sort of this more deep time perspective. So this is, I think, another data set that you're working with. This is the observed Arctic sea ice extent in September. And we just see the loss that's occurred from 1979. This is through last September, so already 2019, pretty long record. These data are also from a satellite, but they're from a satellite that operates at a longer wavelength than the visible wavelengths that we use for seeing, and that those beautiful composites that we saw at the beginning of the talk are made of. And this longer wavelength, the passive microwave wavelength, is really important because it enables you to see through the clouds and really understand if there's sea ice there or if it's open water. So this wavelength is very good at seeing through clouds and really discriminating between sea ice and open water. And this is a very widely used data set. You can get some more context on it from the National Snow and Ice Data Center. You can download the data yourself. I just provide both of these links here in case you want to dive into that more. One of the things that we've, of course, noted in addition to these long-term trends are these extremely low years, and these years really have a overwhelming impact on the Arctic. For example, on ecosystems, on other aspects of the system. And September of 2012 is the lowest Arctic sea ice extent on record. And here, I really like this from Live Science. They've superimposed the area of the Arctic sea ice on North America. And the area in the white is the aerial coverage on this date in September 20th, 2012, which is the lowest amount of Arctic sea ice cover we've ever seen. And then in the light blue, you can see where it would typically be. So you can see this reduction in ice cover is a lot of area. It's, you know, moving from somewhere in northern Mexico to the middle part of the US. These are big retreats, big changes in the aerial extent. And I think sometimes changing the map projection can be helpful for seeing just how dramatic these changes are. So in addition to observations, which we've used and you guys have used to develop your conceptual model, I really enjoyed these questions in the chat yesterday as well about what is a model. I want to introduce another kind of model in addition to the conceptual models that we've discussed. I often use numerical models, and these models just consist of a bunch of equations that are solved simultaneously, often on a supercomputer, that describe relevant climate processes. So they're on a grid, a horizontal grid, a vertical grid, and some of the physical processes that are include radiation, so that you guys have talked about here. They include equations that describe how sea ice melts, how sea ice grows. They include representations of the processes in the ocean and the atmosphere that move heat and moisture around in the atmosphere. They include clouds. They include on the continent things like snow, land cover. So these are very complex models. And I want to make a distinction between the conceptual models that you guys have used and these numerical models. And that distinction is that these numerical models can be used really to test hypotheses, to understand the relative importance of different processes, and to make future projections. And so unlike the conceptual models that we've been putting together as a part of this curriculum, these models are really tools to help you test your understanding in a quantitative way. And many of the features that emerge from the simultaneously solving of all of these equations, they're what I would call emergent. They're not something that you write into the code of the model. So we don't write into the code, you know, make the sea ice go away when we increase the greenhouse gases, right? We just put all of the processes that describe how sea ice works. And then when we increase the greenhouse gases in the model, we see what the resulting processes are that lead to, for example, changes in sea ice. So to make that clear, I thought I would give an example. So I just have two maps here, global maps. On the top, this is the change in the surface carbon dioxide concentration. And here, the unit is just kilograms of carbon dioxide per kilograms of air. And if you look at the spatial pattern here, what you see is, for example, the northern hemisphere has more CO2 than the southern hemisphere. And this makes sense because many of the sources of carbon dioxide are in the northern hemisphere where a lot of the industrial activity happens, just because there's a lot more land mass and a lot more people. And you can even see these hotspots of places where there's more CO2. And the atmosphere is mixing all of this together, but it doesn't mix as fast as some of the emissions occur. So, for example, over Asia and Europe and the east coast of the US in particular, we see these larger CO2 amounts. So what this is it's showing you sort of the spatial pattern of how much CO2 has increased, and it's increased everywhere, but there's definitely these hotspots. And this is provided here as a forcing for the model. On the bottom, this is what emerges. This is the response, right? So here, what we see is that unlike the pattern of where the emissions are the largest, for example, over Asia here, we don't see that place being the place with the largest warming. In fact, the place with the largest warming in these model simulations is the Arctic, and it's warming, 2 to 3 times more than other places across the globe. So this response, this is something that emerges. It's not something that we write into the code of the model. It's just something that comes out of the data out of the solving of all of the equations. Maybe I'm going to stop there and just see if there are any questions, because I think this distinction between numerical models and conceptual models is an interesting one, and maybe you guys have additional thoughts about it. Does it make sense? Maybe give me a thumbs up if it makes sense to you, or if it's still confusing. Thumbs up. Thanks, Turtle.
I have a question, Jen.
Yeah.
I'm just always curious about how the data is collected. So the CO2 is an average over a certain amount of time, or how is that?
Yeah, so that's a great question. This is actually a projection for the future. So this is for how things would change over the 21st century. So there's certain assumptions that have been made here about where industrial activities will happen in the future. Those assumptions, you know, are based on, you know, trajectories and current, you know, demographics. And so there's a lot of assumptions made there. I guess the idea though is that you can make those assumptions. Where will all of these emissions of something like carbon dioxide occur on the planet? But then what this climate model with these equations, you know, solve simultaneously on a supercomputer, what that enables you to do is ask, well, where on the globe are we going to see the biggest impacts? Does that make sense?
Yeah, and is it kind of like a weather model, like when we watch the hurricane models of where they think they're going to go? Is that what you're saying this is?
Yeah, so there's some important distinctions between climate models and weather models. One important distinction actually is the importance of radiation. So, you know, when you're trying to make a projection for how the climate is going to change, let's say over the next 50 years, you have to get the radiation budget right. If you want to make a projection for whether or not it's going to thunderstorm over the Great Plains this afternoon, radiation is probably not your number one concern. And in fact, many weather models, they don't focus on radiative transfer to the same level of accuracy as climate models. So I think an important question to ask with numerical models is this model designed for the task that it's being used for? Yeah.
And just one more question. The movement of the carbon dioxide from, say, over Asia, and then the heating distribution in the next model. I mean, how do you track where the carbon dioxide goes? Is it through modeling wind currents or?
Yeah, so if we look back, I wonder if I can get back. Yeah, basically the emissions that occur, basically they get put into the atmosphere. So let's say, for example, you have a power plant, you know, in the middle of the US that's putting CO2 up into the atmosphere. That's your emissions source. Once it goes up into the atmosphere, the winds, the atmospheric winds, which are predominantly from the west in the mid-latitudes, they'll carry that carbon dioxide and mix it actually pretty efficiently, especially in the mid-latitude. So that's why there was that gradient, that difference between what's happening in the northern hemisphere versus the southern hemisphere. I don't know why. I'm going to just stop my share for 1 second. It's not letting me go back once I'm in presenter mode, which is one of the reasons I don't like going into presenter mode. Let me just try this again. Share screen. So if we look here, for example, let's say we have a power plant. Do you see my mouse?
Yep, we can see it.
Okay, great. So let's say we have a power plant here in the center part of North America. If that power plant results in some emissions of CO2, the atmosphere is going to mix that all over the northern hemisphere. So that's why, for example, if you look here in the northern hemisphere, actually the amount of CO2 is higher than it is over the whole southern hemisphere. And that's because basically the mixing is happening very efficiently in the northern hemisphere, and it's hard for that to mix across the equator. over time, everything gets mixed together though. So that's why even in the Southern Hemisphere, we have these, where there's not a lot of sources of CO2, we still have these large 21st century changes in CO2 concentration. So I guess the short answer is there's a whole sort of model behind how these point emissions are being translated into where the CO2 goes, and it gets mixed globally. And where that CO2 ends up, is not necessarily matching where you're seeing the most warming. So for example, this might be something you would have as an idea, oh, maybe the Arctic has more CO2, and so that's why it's warming more. And you can see here, that's not the case, right? We have the largest concentrations of CO2 over, for example, Asia, and the largest warming over the Arctic.
That is brilliant, Dr. Kay. The correlation that you just made is absolutely brilliant. That's something that I would give to students right at the beginning. So let's look at what it actually creates these CO2 emissions. Where are they located on the planet? I mean, this is really exciting to me because it gives students a chance to be involved real world and say, oh, well, what are some other solutions that might be present in those areas that are creating great emissions? Thank you.
Sure. Yeah. And, if you're thinking about how to teach this and there's like a key graph that you're missing that you would like as a part of, building conceptual models and ruling things out, I'm happy to add additional graphs. We tried to think about some of the things, and I was thinking about this one yesterday. So, yeah.
I was just going to say, I can see this as a phenomena model that students could use and discuss and try and figure out and have questions on. I think that was excellent. Yeah, I enjoyed that too. That was really good. Just interesting.
Yeah, sure, cool. So maybe I'll end with just one last kind of tie-in to MOSAiC, and then we can just open it up for any general questions. So I was involved in a research study that actually used this same climate model to understand some of the projections for where MOSAiC, where the ship in the Arctic might go. And so these very general questions, what are the causes and consequences of the sea ice being younger and thinner? And I just want to say, like, this is a common joke too. Like, don't we all wish we were younger and thinner? Sea ice is going there, blah, blah, blah. Anyways, I just have to put that out there because it's funny. But the consequences of it for planning a field experiment are important. So on the left here, we have a whole bunch of different trajectories that are all possible trajectories. These are based on satellite data of where, for example, a ship that's drifting in the ocean, in the Arctic Ocean, might go. And on the right-hand side, what we have is a projection for those same types of trajectories, but in an Arctic where the sea ice is younger and thinner. And so what you can see here is that, for example, some of the paths for where a ship like MOSAiC might end up, some of the drift paths are really different. For example, some of them end up, in regions where you never saw the paths with the current observations and the current satellite data. And another thing that's true, and maybe a little bit harder to see here, but you can see from some of the calculations for how long it takes for the ship to go along any of these trajectories, is that sea ice, when it's thinner, the ship moves through it more quickly. There's less drag, less resistance. And so actually the ship kind of gets pushed around a little bit more easily by the winds in the Arctic. And so there was a lot more concern in a younger and thinner Arctic that this ship would basically, get pushed out of the Arctic and not be there for the full annual year, for the full year to measure the Arctic. So there's a nice video here that just talks about the results from this project. And so if you have some time later, I encourage you to watch it. You can also download the paper. It's called Going with the Flow. And flow here is F-L-O-E because it's a sea ice flow. but it's tracking the ice in this climate model project, and it's providing context for the ship-based observations. And the first author here is Alice Duvivier, who's the scientist at NCAR, and then the rest of us are here. We were all co-authors on this paper, and it's available for free to download if you want to kind of see how, for example, you might combine insights from a model and from satellites to try to help plan a field expedition like MOSAiC. So I'll stop there, and I'm happy to take questions. I know it's hard sometimes to think of them right away, or maybe it just seems like too much time we've spent already, but I'm always available if you want to send me an email or ask a question over the chat. You know, I'm really excited to see all of you guys here. It's really been the highlight of my week, so thank you.
Thank you so much, Jen. Does anybody have any other questions? All right, well, if you, oh, go ahead.
This may already have been something that you had discussed, but is there a difference, or is there has to be something with the satellites have to determine where the CO2 is, whether it's in the troposphere versus upper layer, lower layers of the troposphere, upper layers of the atmosphere? Does that have to be taken into consideration in the radiation budget?
It does, because the sources of CO2 are often near the surface. So actually this here, this is the surface carbon dioxide mixing ratio. So I just took the surface, the nearest level to the surface, and mapped that. It would look different if I mapped something, for example, at the top of the atmosphere or in the stratosphere. So yeah, I mean, it does. There are processes that mix CO2 vertically as well. So you can think of afternoon convection and storms, for example, doing a lot of vertical mixing in the atmosphere. But yeah, the vertical distribution is another interesting thing to explore, and something certainly that a numerical model that has all of the equations that describe mixing and moving of air, moving CO2 around vertically and horizontally would include.
Thank you.